So thank you very much, Kiao. It's my great honor to be able to speak here in Brisbane in person. And today I'd like to talk about the computer-simulated person for in silico assessment for indoor odor and perceived air quality. First, I would like to start this slide. This is my house and designed by my wife and myself. And my wife is an architect and designed this overall structures. And I'm a researcher and engineer in the field of HVAC systems, heating, ventilation, and air conditioning systems. And I would like to say my house has no privacy. I mean, I have two daughters, but my two daughters complain about no privacy in my house because this house is just only one space, except for the bathroom and toilet. And this is relatively one big space, but in order to reduce the heat load of air conditioning systems, we designed this folded roof shape. This is because to reduce the total amount of air, indoor air, to control by air conditioning systems. And in order to control the air temperature in my house, I introduced two air handling units. One is located at the floor chamber. The other is the upper part of the space. Here, this is one. The other is inside the floor chamber. And in order to control the floor surface temperature, one air conditioning system is used to control the air in the floor chamber. And this means during the winter season, I use the floor heating systems. And during the summer season, we use the upper part air conditioning systems, and relatively low air temperature is supplied from the upper part. And because of the negative buoyancy effects, low temperature controlled air is coming from upward to the downward. And I would like to say here, in this design, I gave up to control the whole room, whole air volume, just focus on the local domain in order to minimize the energy usage for air conditioning systems. Therefore, I must say my background is architectural environmental engineering and a bit far from the computational fluid dynamics analysis inside respiratory system, but I try to do my best to explain my current research activities. Okay, let's take a look at this slide. You can see three room conditions with same air volume and same ventilation systems and same airflow rate. But only the differences of these three rooms is the difference location of scalar generation source, pollutant generation source. My question is, which of the three rooms has the highest concentration? It's not so easy for us to directly answer this question. This is almost the same question. There are the three rooms with same air volumes, same room geometries, same ventilation rate, and same location of inlets. This is a window. And only the difference, and same scalar emission locations, only the differences of these three conditions is the location of exhaust outlet here. You can see three exhaust outlet. I have same question, which of the three rooms has the highest concentration? Firstly, we must define the concentration. And can we estimate the concentration in the room? I mean, for example, if we can specify some point, of course, we can discuss about the point concentration, but it's really difficult to measure or identify the point concentration. How about the whole room volume average concentration? Or how about the local domain average concentration? Or exhaust outlet concentration under the perfect mixing condition? If we know the scalar generation rate and ventilation rate, we can simply calculate the concentration and the perfect mixing assumption using these simple mass balance equations. Of course, all of you can use CFD technique. And then by using CFD technique, we can analyze scalar concentration distributions and know each point concentration. But under the environmental design stage, our architecture environmental design stage, maybe we just know the scalar generation rate as a representative value and ventilation rate. And then we can simply calculate only the perfect mixing concentration. I believe this value is a bit far from some representative point concentration. Okay, here I would like to briefly introduce the index for ventilation efficiency in indoor environments. Of course, if we know the point concentration, a point concentration might be a very good representative or discuss about the, the pollutants level in indoor environments. And second one, ratio of scalar concentration or normalized concentration by using representative concentration. For example, represent normalized by perfect mixing condition. This normalized concentration might be a very useful index because this normalized one can compare with the different, different conditions. Third one is we usually use this concept under the design stage, age of air concept. This is the travel time of fresh air from supply inlet to the certain point of indoor environment. And this age of air distribution is easily calculated by using CFD technique. This means scalar concentration distributions and a uniform entire scalar source. By using this age of air concept, we can discuss about the fresh air delivery efficiency from supply inlet to the certain point. And I would like to emphasize here by using the emission rate, scalar emission rate, and ventilation rate, we can calculate perfect mixing concentration. And by using CFD technique, we can calculate the volume average concentration. Unfortunately, volume average concentration and perfect mixing concentration is not always consistent with each other. Therefore, the ratio of the perfect mixing concentration and volume average concentration shows some representative or useful ventilation rate. This effective ventilation rate is called a purging flow rate, and we usually use the purging flow rate as the main control parameter for pollutants control or contamination control. Okay, I would like to show two simple results for ventilation efficiency analysis. The upper four figures, the same condition, all the same conditions, same ventilation rate and same geometry and same airflow rate. And from the ceiling level, fresh air is supplied, and exhaust air is here is lower level openings. And you can see the concentration distributions. This contour concentration distribution shows age of air distributions, normalized age of air distributions. And fresh air of age of fresh supplied air must be 0. And then 0 fresh air is coming from the supply inlet to the indoor environments. And at the quantum effect, this fresh air is attached to the ceiling, and along with the wall surfaces, air is exhausted. But inside this room, you can see it's very stagnant region. And then the center of this room, age of air in this center of the room will be relatively high compared to the perfect mixing concentration. And the differences of these upper four cases is the inlet condition of turbulent intensity. We set the same average velocity, but the difference is the turbulent intensity from 0% to 30%. Inflow turbulent intensity has significant impact on the flow distributions and also the concentration distributions. But I must to say, I love Land's model instead of the every year simulation because of the very time very time consuming. And this is the result by Land's simulation. Therefore, including some uncertainties. By using this ventilation efficiency analysis technique, we can analyze the age of air distribution inside respiratory systems. You can see the individual differences of three airway models, model A and model B and model C. And this is the steady state inhaled conditions, and analyze the age of air distribution. The fresh air is coming from the nostrils and through into the edge of this model. And you can see some differences of age of air distributions. And furthermore, there is some hotspot. I mean, hotspot means the very high value of age of air. For example, here and here, the hotspot of lower age of air is not consistent each other in the three models. This might be some personal or individual differences. By using this technique, this is the indoor ventilation efficiency index for indoor environmental design, but this index can apply to the clarifying the ventilation efficiency inside respiratory systems. And I would like to show one more result is for analyzing the age of air distributions in human models and rats and dog and monkey. And this rat model is called the Kiao's groups model. I use thank you very much of Kiao. And you can see the left-hand side figures. Vertical line shows the normalized age of air, normalized by nominal time constant of each respiration conditions. And in case of the human model A and human model B, this green bar shows the whole average age of air, fresh air delivery efficiency for whole upper airways. And yellow shows the average age of air at the olfactory region, and green one shows the pharynx regions. And we can confirm significant differences of age of air value at whole upper airways and olfactory regions and pharynx regions. I would like to emphasize, in case of human model, I'm not sure about the prediction accuracy, but I would like to emphasize in our model, compared to the average value of age of air at whole upper airway, olfactory region is maybe advection dominant, and age of air will be very low compared to the other regions. And compared to human model, please take a look at the results of dog model. In case of dog model, very high age of air at olfactory region. This is, left-hand side is inhale conditions, and right-hand side is exhalation conditions. In case of inhalation conditions, inhaled air is transported. In case of dog, inhaled air is very slowly transported to the olfactory region and stay longer. This is the maybe differences of mechanisms of perception. One of the reasons of the perception of olfactory perception between dog and human models. And furthermore, in case of exhalation conditions, age of air distributions, age of air value has significant differences between compared to inhalation conditions. And this means in case of exhalation mode, the air coming from the deeper side is smoothly passed through the nasal cavity, smoothly passed through the olfactory region. But in case of the inhalation, the inhaled particles or scalar will relatively stay longer at the olfactory region. Okay, from this slide, I'd like to briefly introduce the history of in silico human model or computer simulated person development for indoor environmental design. And maybe you can see various types of in silico human model, computer simulated person for intended to integrate to the computational fluid dynamics analysis. to the best of my knowledge, the pioneering work of this development of in silico human model was done by Professor Kato and Professor Murakami's group, University of Tokyo, my former supervisor, start from the 1990s. And a lot of researchers proposed a fruitful model for reproducing the human geometry. And this is our current models and precisely reproduced the human geometry and integrated the airway model from NASA or ORL to the 16th bifurcations. And one of the objectives of this types of computer-simulated person is to analyze the summer comfort or summer sensation of residents in indoor environment at the design stage, and also to predict precisely the inhaled or dermal exposure of chemicals or pollutants in the indoor environment. And then maybe you can see this slide. One of the objectives of air conditioning system is to control the skin surface temperature, and then the one of the very important objective is to for this computer-simulated person is to precisely analyze the skin surface temperature distributions in addition to the flow characteristics around the human body. And I would like to say one more thing. In order to validate this accuracy of the computer-simulated person, we usually use the summer mannequin system. Therefore, this type of virtual mannequin is computer-simulated person is one of the digital twin model for summer mannequin experiment. Okay, this is a very simple simulation results for transient carbon dioxide concentration distribution inside a very small enclosed work environment. And left-hand side is the transient analysis of CO2 concentration distributions around human body. And in this analysis, we integrated the gas exchange model between oxygen and carbon dioxide at the end of the trachea region and reproduced the acid breathing cycles. And at the start of this simulation, CO2 concentration controlled at 400 ppm. And during the simulation, CO2 concentration overshooting 1000 ppm. I'm not sure about the guideline concentration of CO2 in Australia, but generally speaking, in Japan and other European countries, we usually set 1000 ppm as a guideline concentration value in indoor environments. Unfortunately, in this case, is CO2 concentration around human body exceed 1000 ppm under the enough sufficient ventilation rate supply conditions. Right-hand side figure shows the transient simulation of temperature change in indoor environments. A human body is a heat engine, heat generator because of the metabolic heat generation. Therefore, relatively high temperature distributions formed around human body because of the summer plume around human body. I would like to say the CO2, especially CO2 concentration, if the average or representative concentration is precisely controlled under 1000 ppm, unfortunately, our exhalation air contains approximately few percent CO2 concentration. Therefore, relatively high concentration CO2 concentration field is formed around your face. And this is one more simple simulation results for using computer-simulated person and computational fluid dynamics analysis in indoor environments. This is the case of displacement ventilation systems, and then fresh supplied air, relatively low temperature air is coming from the lower side along with the floor level and exhausted the ceiling levels. And in this case, I set the inlet velocity at 0.1 meter per sec, very low velocity, and also set the emission source at the floor levels. In this case, I set the formaldehyde emission flux constantly along with this floor level. And you can see some shift in results. Here, you can see the summer plume and upward trend flow because of the heat generation of human body. I would like to emphasize based on our simulation, numerical simulations, the maximum velocity at the top of our head is reached at 0.25 meter per second. This is a 2.5 higher velocity compared to the inlet supply velocities. And furthermore, of course, we must say the heterogeneity of non-uniformity of flow distributions around the human body, and also as for the whole formaldehyde concentration distributions, very heterogeneous concentration distributions around the human body is formed. And I would like to ask again, what is the representative concentration in this scenario? WHO defined the guideline concentration of aldehyde at 100 microgram per cubic meter. And in this simulation, we carefully set the total emission rate of formaldehyde from floor level and supply fresh air from ventilation systems. And then the perfect mixing concentration of this analysis is controlled at 100 microgram per cubic meter. Therefore, this is the mass balance concentration, and exhaust outlet concentration of this simulation is 100 microgram per cubic meter. By using this flow field analysis and scalar transport analysis, we can finally analyze the volume average concentration of this room. And in this case, room average concentration for whole room is 91.1 microgram per cubic meter. This means 10% lower compared to the perfect mixing concentration. I would like to emphasize by using the effective ventilation systems, in this case, is displacement type ventilation systems, very effective, 10% effective compared to the perfect mixing type air ventilation systems. This means that we can reduce 10% of energy use or power use. And furthermore, by using computer simulated person with respiratory system, we can calculate or estimate inhaled air concentration of formaldehyde at nostril openings. In this case, the concentration was 62.7 microgram per cubic meter. This means 40% lower concentration value compared to the perfect mixing concentration. If the controlling target of air quality at nostril level, in this ventilation system can reduce 40% energy compared to the mixing ventilation system. But unfortunately, in this case, it's human model is just a solid and standing and no movements. Therefore, a lot of uncertainty. But by using these types of simulation, we can feed back to some very important information to the HVAC design. Therefore, the overarching objective of our study is to develop these types of method, multi-stage optimization method of total local environmental quality. Local means skin surface temperature or dermal exposure or inhalation exposure by using in silico human model as a sensor for the HVAC systems. Okay, this is the introduction of myself. And today, mainly I would like to talk about the smell, odor in indoor environments. And now I'm in charge of a convener of ISO TC146 SC6 working group 25. And ISO TC146 is focusing on air quality management. And SC6 subcommittee 6 is treating the indoor air. And working group 25 is now establishing the ISO 60044 test method for measuring perceived indoor air quality for use in testing the performance of gas-based air cleaners. And of course, we can measure the concentration differences of in and out of air cleaners by using chemical measurement technique. But in this standard, we focus on the evaluation by central evaluation by human panels. The principles of measuring perceived air quality is shown here. The perceived air quality, this means the smell of air, is determined using subjective evaluation of acceptability and odor intensity. And the air assessed by a panel is presented via sniffing device, a funnel-type sniffing device. And left-hand side of figure shows the acceptability scale from clearly unacceptable to clearly acceptable. And panel check like this after the one sniffing. And odor intensity scale with category scale is shown here from no odor to the overpowering odor. And panel check like this after the one sniffing of the indoor air. This is the test conditions of ISO 60044. The panel member shall enter the this test room consists of two chambers. First one is the test chamber, including odor emission source and air conditioner, air purifier. The second one is the anterior front space in which human panel enter. And the panel member shall enter the front space and assess quality of air presented via sniffing device. This is the sniffing cone or sniffing device immediately upon arriving at the measuring point. And measurement shall be made after taking one sniff of the air, prohibited to 2 or 3 or 4 sniffing, just only one sniff. And only one measurement shall be made at the time, either acceptability or perceived odor intensity. My question is, one sniff is enough for evaluation of the odor intensity or acceptability? Okay, this is the perception of odor and smell. All of you are specialists and of olfactory epithelium substructure, and then I would like to skip the detailed explanation. But in order to discuss about the these types of perception, we have two approaches. First one is the sensory experiment by using the human panels. And second one is CFD-based in silico approach. Of course, I know by using sensory experiment by human panels, we can provide direct result of evaluation perceptions. But I know we have a very strict ethical constraint. This means we cannot provide very high concentration because of the ethical constraint. Therefore, supplementary CFD-based in silico approach can contribute to the elucidating of the mechanisms of chemical pollutant transfer from outside to inside nasal cavity. In order to discuss about the input information of chemicals in epithelium tissue surfaces, we must carefully consider about the boundary conditions between lumen and tissue surfaces. This is a very simple modeling of deposition velocity of scalar transport inside nasal cavities. From the molecular theory, the surface deposition of the local scalar concentration close to the surface can be described by using this formula. And gamma in this JS means the deposition flux, and gamma means the mass accommodation coefficient or reaction probability between the chemical molecules and target surfaces. And V bracket shows the Boltzmann velocity. And then if we can calculate the gamma and Boltzmann velocity, we can apply to this deposition modeling into the shift simulation. But unfortunately, this model is true within the range of molecular free paths, and compared to the CFD mesh, molecular free path is much, much smaller. And then in order to apply this model to CFD grid, the first grid point at the viscous sublayer, we usually use this type of damping function of the molecular diffusivity into this flux model. But here I have one question. In this case, is this deposition flux is defined by the air phase only air phase concentration and not discussed about the surface concentration. If this is diffusion flux, generally speaking, we must consider about the potential differences, gradient of concentration. But in this modeling, the information of surface concentration is indirectly integrated into the gamma value. And this means this concept is assumed to the hypothetical zero concentration surface and maximize the concentration gradient at the vicinity of the wall surfaces. We know in case of the precise analysis of diffusion flux at the vicinity of the wall surfaces, we must consider about the adsorption isotone between target chemical compounds and surfaces. And you can see the representative adsorption isotone. And generally, we use the linear model called the Henry type model, but Henry model can apply within the very low concentration range. And of course, other adsorption isotones show some logarithmic or very complicated profiles as function of the concentration. And in some cases, we must consider about the hysteresis of these adsorption isotones. But it's very difficult for me to integrate this adsorption isotone into the simulation of scalar analysis inside another cavity. In this analysis, we simply use the linear model as a function of the adsorption isotone. Here, I'd like to briefly introduce the PBPK model, physiologically based pharmacokinetic model, in order to precisely analyze the equilibrium concentration between lumen and tissue surfaces. Objective is to analyze the more precise analysis of deposition flux, adsorption flux from air phase to the tissue surface phase and equilibrium concentration at the surfaces. And this is outline of the PBPK model. At the boundary, we must consider about the flux conservation as shown in the upper first equations. And the second equation shows the governing equation, transport equations of scalar in mucous and epithelial tissues. And third one shows the transport equations of scalar chemical compounds in submucosal tissues. And in order to convert the concentration unit from, for example, air concentration to the concentration in tissue, I mean for example, microgram per cubic meter air concentration must change to the microgram per kilogram tissue in this model. And then I introduce the partitioning concept as shown here. It's a very simple linear model. It's called as the Henry model. And in this, from this, I'd like to show some simulation results, but in this case, I focus on the left-hand side PBPK model for local side. And you can see the last governing equations here. This is pollution of chemical compounds into blood. And this blood concentration is one of the objectives to analyze by using the PBPK model. And this blood concentration will be a very important input information for whole body PBPK model. But here, I'd like to show the left-hand side results. By using this PBPK model integrated with computational fluid dynamics technique, we can analyze the equilibrium concentration between lumen and tissue surfaces as a function of time. We can predict the fluctuating equilibrium concentration and also the time-dependent change of concentration distributions inside the tissues, as shown in the examples. Here, this is the in silico human digital twin model for reproducing the ISO experimental conditions of ISO 60044. In this case, I adopted very simplified PBPK model as a boundary conditions of inner tissue surfaces in respiratory systems. And we conducted the integrated analysis of flow, heat, moisture, and odorous chemical compounds. Here, I'd like to show the result of acetone case. And this here, this graph shows these results shows the relationship of indoor air enthalpy and acceptability or percentage of dissatisfied reported by human panels. This is reported by 1998 by Professor Panger or Panger's group. This is very old, but still very important result, I believe. The enthalpy of indoor air will affect odor perception. In this case, is as the enthalpy of indoor air increases, acceptability decreases, and percentage of dissatisfied increases. Therefore, in order to discuss about the odor perception, we must consider about not only chemical transport, but also the heat and moisture transport inside the respiratory system. Okay. And in order to analyze the conductor integrated simulation of heat and moisture inside human body and outside surrounding human body, we introduced conducting integrated analysis of thermo-regulation model for skin surface temperature and core temperature analysis. And I would like to skip the explanation of detail of this model, but we have several types of thermo-regulation model to predict the skin surface temperature distribution and core temperature, deeper side temperature in human body. This is the Hygrothermal transfer modeling in respiratory tract. In our simulation, we used this total heat balance equation of airway walls, a very simple heat transfer models. And as for the water vapor concentration, we simply set the representative surface concentration by using this formula. And by using the thermo-regulation model, we can calculate the core temperature inside human body. Therefore, core temperature might be your input boundary conditions of this heat transfer analysis of respiratory systems. This means, we conducted integrated simulation of thermo-regulation model to control core temperature and skin surface temperature as a function of surrounding indoor environment, and heat and mass transfer analysis inside the respiratory system in addition to the scalar transport analysis. This is the cases analyzed of our CFD simulations. You can see the computer simulated person in anterior rooms and sniffing devices. And in this case, we focus on the acetone as a representative odorant, and concentration of acetone is controlled at 100 microgram per cubic meter, and flow rate via sniffing device is controlled at 0.6 liter per second according to the prescription of ISO 60044. And I would like to say again, I love LAMP model. Therefore, in this simulation, we adopted SSTK omega model for transient analysis. And I know the limitation of the prediction accuracy of LAMP modeling, but I choose the stability of CFD analysis. And in this CSV model, skin surface is controlled by the thermo-regulation model, and the supply inlet of this anterior room is controlled under at the 23 degrees C air temperature and 50% RH. This is prescribed by the ISO 60044. Okay, this is a simulation result of transient acetone concentration distributions. And at the calculation start, t equals 0, acetone is coming from the bottom of this sniffing device at the 0.6 liter per second and with 100 cubic meters and start breathing. We can see it's very transient heterogeneous concentration distributions of acetone at the face are formed. And here, this is the simulation results at third breathing from 8.1 second to 12.15 second from the simulation start. And left-hand side shows the acetone concentration distributions at nostril during the inhalation conditions. And there is clear concentration distributions of acetone at the nostril openings because of the potential flow formed around this opening. And this means the this blue zone is the contribution of indoor air, not the acetone-contained air from sniffing device. During the inhalation period, because of the these types of potential flow, we usually induce the indoor air from upper part to the nasal cavities. And right-hand side figure shows the concentration distribution of acetone during the exhalation conditions. Relatively uniform concentration of acetone will be exhaled via openings, nasal openings. Okay, I would like to talk more about the fresh air or air delivery from nostril opening to the olfactory regions. Compared to these distributions, the incoming fresh indoor air is smoothly transported to the olfactory region because of the maybe quantum effect and no strong mixing. This means our perception of acetone will be strongly affected by the concentration distribution of this inhaled air. And furthermore, by using these types of simulation, because of the differences of size of nasal cavity, left-hand side nasal cavities, and differences of flow resistance, the airflow rate and total amount of inhaled acetone via each nasal nostril opening will significantly difference. Okay, this is a time series of equilibrium concentration of acetone at the lumen and tissue surfaces. You can see the significant fluctuation of the equilibrium concentration of acetone at surfaces. This is the result of the olfactory epithelium. And I would like to say 2 points. First one is at the first breathing, because of the air mixing of indoor air, very low acetone air is inhaled. The second, after the second breathing, maybe almost the same, reproduce the same concentration profile, but we can see two peaks during one breathing. This is the inhalation, and this is the exhalation. And this is the overlapping the experimental results by Professor Fanger's group. This left-hand side vertical axis shows acceptability, and horizontal axis shows the number of breathing, respiration time. And here, Fanger's group emphasized the acceptability or perception of smell is very sensitive, and then at the first breathing, one sniffing results show the minus 0.2 acceptability. This is a negative level of the acceptability. But second breathing, here, the third breathing and fourth breathing and fifth breathing, during just only fixed breathings, the perception will be going to the equilibrium. This is caused from the olfactory fatigue. But unfortunately, our simulation cannot reproduce these types of one. Okay, this is the time trend transient analysis of acetone adsorption flux on mucous surfaces. Okay, I would like to say 3 points. First one is the differences of first breathing, respiration, and second breathing, and significant difference. And second point is this red color shows the adsorption flux onto the olfactory region, and blue one shows the other regions. We can confirm the significant differences of flux trend, profile of the flux, especially in case of the flux on olfactory region. Can observe two peaks here, inhalation and exhalation. Maybe this is the also nasal pathway. This is the retronasal pathway. And unfortunately, except for the olfactory region, we cannot confirm the second peak during one breathing. This is the significant differences of the region of olfactory region and other regions. This is the in silico study, and then we can easily change the target chemical compounds. The upper part is the acetone result, and left-hand side, lower left-hand side is the acid, acetic acid, and this one is ammonia. By applying these completely different boundary conditions, we can calculate these types of trend of flux and show significant differences of each other. Okay, this is the differences of breathing cycle. Left-hand side is the general breathing cycle, and right-hand side is the sniffing cycle, short and strong breath for one time. And this differences of breathing and sniffing cycle significant impact on the change on the flux profiles. And I'm not sure which breathing cycle had good for a subjective evaluation, but I'd like to say the total amount of flux and profile has significantly different each other. Okay, this is the rough result of the contribution ratio of acetone distributions. And if we assume this means the 28% of inhaled acetone was exhaled via nose opening during one breathing, and 40% of acetone adsorbed on mucous surfaces, and 50% is transported to the lower part of the airway systems. And this is the result of the hygrothermal transfer analysis. And upper part is the evaporation flux during 3 breathing cycles, and lower figure shows acetone flux and significant differences of each other. And I'm not sure about this relationship, but maybe we can provide some fundamental information by using this integrated simulation. Okay, because of the time limitation, I would like to skip examples. California State Research Institute asked us to check the cannabis smoking, and we reported the impact of cannabis smoking by using e-cigarette device. And I'd like to say the cannabis is no difference of the, in terms of the absorption, cannabis is no significant differences with nicotine. Sorry, this is the conclusion of my talk. At present, absorption flux and sensible and latent heat flux to olfactory epithelial tissue may be analyzed quantitatively, but I'm not sure about the prediction accuracy. But their combined effect of acceptability and perceived odor intensity variation could not be analyzed, unfortunately. Olfactory fatigue is also numerically unpredictable. This might be a very challenging issue. And hence, still we do not know how many sniff would be appropriate to alter odor evaluation. But according to the expert from Denmark, After all, FDI's version of ISO 60044 stipulate one time in one sniff in accordance with, yes. Thank you very much.
It's wonderful and very comprehensive presentation, Professor. Thank you very much. I'll ask the question, and I also want to make some comments. So the question is very interesting presentation. I may have missed it, but what are the differences between old air and new air?
So what's the meaning?
What's the difference between old age of air and new?
Sorry, age of air concept means the just a travel time of fresh air. Therefore, the new air means the upcoming supply air from supply inlets, and old air means the long time travel air from supply inlet.
Okay. So yeah, so this age of air is borrowed from the building HVAC people, and I think we can really bring it into respiratory airway because you can determine the freshness of air reaching certain anatomical regions. And I hope that maybe future simulations by people will start to include age of air, particularly if you've got virtual surgery or post-surgery. If you've had post-surgery, you want to see where the freshness of air is coming. So age of air can be really useful for that. So thank you for sharing your HVAC skills. And the deposition of formaldehyde is a key, can be used as a key indicator for gaseous drug deposition. So if we develop new drugs that are in gaseous form, it will behave very similar to the formaldehyde deposition that Ito has demonstrated. So thank you.